you. So, in the last class, we have been discussing about the mixing and phase separation in the context of liquid solutions, more specifically a binary liquid solution containing a solute and a solvent. So, today I will take it further. First talk about some graphical interpretation of the same thing, and then we will talk about how can we get the osmotic pressure and chemical potential also in terms of what we defined as the Helmholtz free energy density. So, what we have discussed so far is if we mix, for example, two solutions, one containing a volume fraction phi1 of solute and in a beaker of volume V1, another one containing some other volume V2 having a volume fraction phi2 of the solute, they would form a homogeneous mixture having some volume fraction phi and a net volume V, where V is of course V1 plus V2, if the free energy in the final state is lesser than the sum of free energy in the individual previous states. So, we talked in terms of the Helmholtz free energy. Just to recall, we said that the Gibbs free energy can be written as volume multiplied by P plus F of phi t, where this particular function F is known as the Helmholtz free energy density. So, if we look at the individual states and multiply the volume with the function f at a constant temperature, so we do not care about the dependence on temperature, just for simplicity in notation we can also put a temperature dependence. So, the sum of these two states, the free energies are V1 f phi1 plus V2 f phi2. If this is higher than V f phi, or on the other hand, if the final state free energy V of f phi is less than the sum of the previous states, then the mixing will occur. What we can also do is we can find the final volume fraction in terms of the initial one using the material balance over the solute. So, we have two equations to solve for phi1 and phi2. If you solve, what we can get is the phi is where I can define x1 as the ratio of the volumes V1 by V1 plus V2. Okay. Then I said that the reverse of this can happen, that is, we can start with a volume phi or volume V containing a solute volume fraction phi, and this can then phase separate into two layers, a bottom layer with a volume Va and volume fraction phi a, and a top layer with volume fraction phi b and volume Vb. Again V is equal to Va plus Vb. So, this will happen, the phase separation will happen again using the free energy criteria, that is opposite of what we had earlier in the case of mixing, that is the free energy in the final state, free energy in the homogeneous state is higher than the free energies summed in the phase separated state. Okay. So, to put it simply, the mixing or phase separation is given by a free energy criteria, whichever direction will lead to a decrease in the free energy that would happen. So, if the phase separation results in a lowering of free energy, the system will phase separate. On the other hand, if mixing leads to a lowering in free energy, the mixing will occur. Okay. So, now until so far we have not really bothered about what that function f is, right. Means it can be any kind of function. Of course, it will depend on the system under consideration. It will depend on, for example, the interaction between solute and solvent and things like that. But still, if I know the particular form of function, I can suggest whether the system has a tendency to mix or to phase separate. Okay, so now we also can look at the graphical interpretation of the same thing without even knowing the function form f of phi. Just by looking at the graph, we can already say whether we have the tendency to mix or to phase separate. So, let us try to look into that. So, what I claim is, again I am doing for a constant t just to make simpler representation, but the idea applies in general. So, if I plot f of phi versus phi, and if the graph is say an upper concave, that is it has a minima like this. So, if it is an upper concave graph, I claim that the system will have a tendency to mix together. And why is that? So, let us say we mix two concentrations phi 1 and phi 2 on the graph. Then if I look at the corresponding value of the function, they will be f of phi 2 and f of phi 1. If I connect these 2 points on the graph, if I connect these 2 points on the graph and look at any point intermediate on this particular line, this corresponds to x multiplied by f phi 1 plus 1 minus x multiplied by f of phi 2, and this we can justify in the following way. So, let us say we look at this particular thing, and let me say that this is my x and this is my 1 minus x. It should be like something multiplied by x, something multiplied by 1 minus x, because the length of the line will not be 1, but that does not really matter. So, you can think of like alpha multiplied by x, for instance, and alpha multiplied by 1 minus x, for instance. And let us say what we have here, let us say I call this some f. Okay. Then by using the similar triangle relation, we know that if I write segments as A, B, C, then and I call these points as they are. So, I know that by similar triangle relation, let me call that point D, we know that BC divided by BA, that is the length from here to here divided by the entire length of the line, is equal to CD divided by AE that I have just drawn here. Okay. Now, we know what BC is. BC is alpha multiplied by x, BA is alpha multiplied by x plus alpha multiplied by 1 minus x. So, it is alpha. CD is simply f of phi 2 minus f, and AE is simply f of phi 2 minus f of phi 1. So, of course, alpha cancels out, and then we get x multiplied by f of phi 2 minus f of phi 1 is equal to f of phi 2 minus f. This if I solve, I will get f is equal to x of f phi 1 plus 1 minus x of f phi 2. Okay. And now, we have already discussed that for phase separation to occur, f of phi should be less than x of f phi 1 plus 1 minus x of f phi 2. This entire thing is my capital F in the figure. So, if the function value is less than capital F, then we know that the system has a tendency to mix together, which is indeed the case, because if I think of any intermediate value between phi 1 and phi 2, of course, if I mix these two liquids at phi 1 and phi 2, the new mixture will have a volume fraction intermediate between phi 1 and phi 2. So, it will lie somewhere in between, and this point is always lower than the point C. So, if I connect A and B, I get a line. The function value must be lower than that particular line because of the concave shape of the graph. Okay. So, let us say this is what I get after mixing. And let me call this point G for instance. Then we know for always that C will be higher than G, and if I think of the corresponding function value, which is f of phi now, that means that f is always higher than f of phi, or f of phi is less than f. Okay. So, if the graph has a upper concave shape, we always have this particular relation that the function value is less than this. Now, you can think of any particular value of x, it does not really matter what x we choose. We always have this thing that if I connect the 2 points by a line, the function value will always be below that particular line, okay, as long as the graph is upper concave. Let us see like what happens if the graph is opposite of this. Let us say we have a convex graph that has a maxima as opposed to a minima. So, now again if I think of two values, phi 1 and phi 2, again I can do the same construction. Now, if I think of any value in between, so this is my f of phi 1, this is my f of phi 2, and then this value becomes my x multiplied by f of phi 1 plus 1 minus x multiplied by f of phi 2, that is my capital F now. Now, you can see the function value is always higher than this particular point, that is always true in the case of a convex graph. This is just opposite of what we had for a concave graph. Okay. So, in this case we always have f of x phi higher than x of f phi 1 plus 1 minus x of f phi 2. What this means is, if the graph is upper concave, we always have mixing, and if the graph is convex, we always have phase separation. Now, we know from calculus that the concave graph must be for the cases where the second derivative of the function is higher than 0. So, graph possesses a minima only when the second derivative is higher than 0. On the other hand, the graph will be convex or possess a maxima if the second derivative is less than 0. So, irrespective of the actual form of the function, if we know the second derivative, we can tell about the mixing and the phase separation behavior, and that is where this whole idea of the using the Helmholtz free energy density becomes useful. So, this single function can tell you about whether the system has a tendency to mix or to phase separate. We only have to look at the second derivative of the free energy. So, now we will take it further and try to discuss two other concepts that we encountered in thermodynamics, that is osmotic pressure and chemical potential. Using chemical potential, we typically talk about phase equilibrium. Okay. So, now I want to illustrate that how these two concepts relate to the definition of the f of phi that we have discussed. It turns out that I can write the osmotic pressure and the chemical potential also in terms of this particular function, and that really makes our job easy, that if I know the function f of phi, I can get all the thermodynamic quantities that I care about. So, let us first look at what the osmotic pressure is. The typical way how osmotic pressure is defined in texts is the following. So, you have a chamber that contains a semi permeable membrane on one side of chamber. You have a solution containing solute particles. So, this is a solution. On the other side, you have a pure solvent that contain no solute particle. We can think of the volume of the solution side to be V, and if I think of the total volume as V tot, the volume of this side is V tot minus V. And now, what is typically said is that the semi permeable membrane, first of all, does not allow solute to pass through, but allows solvent. The best way to think of it is the RO setup that we have at homes. It allows the water to flow through, but not the dirt particles. Okay. But in that case, we apply an external pressure. Here what we discuss is a slightly different idea. But the membrane here in this case can really move across the chamber. It can go to the left or to the right, but the solute particles cannot pass through the membrane, and this is typically practically happening when, for example, the membrane is composed of a porous media that does not allow larger particles to pass through. Solute, if they are like larger molecules than compared to solvent, this is typically an easier way to think about it. So now, to maintain the solution at a constant volume V, we do need to apply an external pressure pi, which we call as an osmotic pressure. Okay. This is typical way we think about osmotic pressure, that there is a membrane in between that does not allow the solute particles to pass through, and the membrane can translate to the left or to the right, and to maintain the solution at a constant volume we need to apply an external pressure, and that pressure is my osmotic pressure. Now, there is a slightly different way to think about it, and that is, there is no membrane. Let us say we have a room containing, say, a closed room, and let us say smoke starts coming in from one end of the room. We can also think of osmotic pressure by the fact that the smoke has the tendency to fill the entire room. So, if I want to keep the smoke right there, I need to apply a pressure on the smoke such that it does not mix with the entire room. Okay. So, the whole idea of semi-permeable membrane, the whole idea of the semi-permeable membrane is hypothetical. We do not need to think about it. We can think of that we have some hypothetical line separating the solute phase and a solvent phase, and that hypothetical line is pushed by the solution phase because of the presence of solute particles. Okay. So, when the smoke is coming in, smoke is pushing into the air, and this pushing in is what is I refer to as osmotic pressure. So, I have to apply an external pressure opposite to that will basically prevent the smoke from filling the room. Okay. So, I want to call this chamber as a hypothetical membrane which can go this way or that way. Okay. So, the only way we are differentiating with what is normally given in books is we discard the idea of a membrane. We think of a boundary separating the solution phase and the bulk, and that boundary will move into the left or to the right, or in 3D it can move in any direction, and to prevent that to move that movement we have to apply an external force. So, in that kind of a language, osmotic pressure becomes a measure of the mixing tendency. If osmotic pressure is higher, that means the system has a tendency to mix. Let us say smoke is coming in and is pushing it with a large pressure, that would mean a large osmotic pressure. That means smoke has a tendency to mix in with the air present in the room. On the other hand, if the smoke had a lower osmotic pressure, then smoke will have lesser tendency to mix with what is present in the room. Okay. So, in that kind of a context, we can think of high osmotic pressure pi as higher tendency of mixing And now, since f of phi that we have discussed earlier, f of phi t that we have discussed earlier, the Helmholtz free energy density already characterized the mixing behavior, that should also characterize the osmotic pressure. So, this is a qualitative way to look into this, and now we will do a derivation of why it is indeed the case. So, let us now say that the total energy of system that I have just drawn is, say, f of dot V. So, if I am moving the membrane, the hypothetical membrane, by say a small volume dV, the work done is my osmotic pressure multiplied by dV. So, if we move, again I am using the word hypothetical, semi permeable membrane by dV, that is dV to the right, is positive to the right, then we do the work. Minus pi dV on the system, just because they are in opposite direction. If we think of work done by the system, it is pi multiplied by dV. So, then pi should be equal to minus dou F dot by dou V, because the change in the free energy is the work done. Okay. So, now let us think of like what F of dot is. So, we have two sides of chamber. One side has a volume fraction phi of solute and a volume V. The other side has a volume fraction 0 of solute, it is a pure solvent, and a volume V dot minus V. So, using the idea that we have discussed earlier, if I think of the total Helmholtz free energy, that is F dot, that is the function of V, is equal to V multiplied by F of V plus V dot minus V multiplied by F of 0. So, I am simply multiplying the volume with the Helmholtz free energy and adding up for the two sides. And now, if I use the definition of phi, that is the number of solute particles multiplied by their specific volume divided by V. So, I can write F of dot V from here. So, I am simply replacing the capital V in terms of phi. So, we have capital V is equal to NP Vp divided by phi. So, I will plug in that value of capital V in the equation I have written earlier, and I will have okay. So, now we know that pi is minus dou F dot by dou V. So, I have already replaced V, capital V, by phi. So, I can write this as minus dou F dot by dou phi and dou phi by dou V. Here dou phi by dou V is given by minus NP Vp by V square, using the relation that we started with, which again I can write in terms of phi as the following, which is minus okay. So, now and dou F dot by dou phi using the relation I have just written. So, if I look at the first term, that is Np Vp multiplied with phi multiplied by f of prime minus f of phi multiplied by derivative of phi, that is 1, divided by phi squared, that becomes the first term, and the second term f of 0 is anyway a constant. So, we have okay. So, now if I put that thing back here, you will see that Np Vp will cancel, and what I will have is phi square the following, which I can simplify, and then I will get the expression so that tells me that if I know the function f of phi, I can also get the osmotic pressure. And the reason why it is happening, because osmotic pressure in the end is something that characterizes the mixing tendency anyway. The higher osmotic pressure means higher mixing tendency, and we can also look at mixing in terms of f of phi. So, both qualitatively and quantitatively we have shown that how we can write osmotic pressure again in terms of same variable. So, if I know the function f of phi, we still do not know it yet, but if I know the function f of phi, I can also get the osmotic pressure. In the next lecture, I will also show that the same applies for the chemical potential, and actually we can do the entire thermodynamics of solutions using a single function f of phi. So, with that I will stop here. Thank you.